WhatsApp is something that I'm now connected. But yeah, email is also on, so I should be looking at it.
Yeah, now it is
Sir,
live streaming.
live started. Yeah,
live started. So we can start now.
So very good afternoon to one and all present here. So we have entered the third module of the lecture series, that is on atmospheric radiation. So I request Professor Someshwar Das, Secretary, South Asian Meteorological Association, to welcome the panelists as well as the participants. Over to you, sir.
Thank you very much, Dr. Lakshmi. A very good afternoon, AVM, Dr. Tyagi Saab, the President of SAMA, Dr. Singhe Dorji, Chief Meteorology Officer of the NCHM, the National Center for Hydrology and Meteorology in Bhutan, and also he's our advisory panel member of SAMA. Dr. V. Mukhopadhyay, Mr. Mukhopadhyay. He is the speaker of today's lecture. He's the retired ADGM from IMD. Members of the advisory panel, or supporting team, organizing team, Dr. Mohan Kumar, Dr. Bhavar, Rohini Bhavar, and all the participants. We welcome you on behalf of the South Asian Meteorological Association, SAMA, and SRM Institute of Science and Technology, Chennai. As you know, today is the 9th lecture in the series and first lecture on the atmospheric physics submodule on atmospheric radiation. As you all already know, the entire lecture series is designed for capacity building of the people of this entire South Asia, plus also the other countries who are the members of our institutional members like NAM-SNT, UC-MODE, and RIMES. So altogether, more than 2,000 people have registered for this course from more than 48 countries. We have a distinguished panel of very senior professors and scientists from reputed institutions of this region who are experts in the field. And they have already delivered 8 lectures so far on the fundamentals of the subject. The lecture series, as you know, is targeted to the postgraduate students and professionals of non-meteorological background who are interested in learning the subject of weather and climate sciences for research and operations. We have already announced earlier that certificates will be given to the participants who have registered for the course and will complete the entire course with at least 75% attendance and a successful performance in an evaluation test which will be conducted at the end of the course. And accordingly, according to the performance, the gradings also will be given. The lectures are live streamed, as you know, on the YouTube channel of SAMA. So they will be available afterwards on the YouTube for those who could not attend the course live. We shall try to have more interactions between the speaker and the participants in this lecture series. So please write your questions in the chat box. Our moderators will pick up the questions at the end of the talk and they will be answered by the speaker. So enjoy the lectures and all the best. On to you, Dr. Lakshmi.
Thank you very much, sir, for welcoming the panelists and participants, also for briefing about the lecture series. So now I request Professor Ajit Tyagi, sir, President, South Asian Meteorological Association, to provide the relevance of this lecture and lecture series. Over to you, sir.
Thank you, Lakshmi, and very good afternoon on a holiday in India and neighboring countries. Wish you a happy, colorful Holi. Well, as Somesh has already given the background of the lecture series, it is essentially a capacity building initiative of SAMA and the SRM IST we have conducted initially 4 lectures. The orientation lectures talks were delivered by the eminent experts from the respective fields, that is the Met Services, India Met Department, DG. Then we had presentations from Professor Somesh, Professor Dash from IIT Delhi on research opportunities, and also a presentation from the NRL about the observing systems, followed by the core modules on atmospheric physics. The first module on atmospheric thermodynamics was taken by Professor Bhaskar Rao sir, who is also attending, and I welcome him, followed by today's series of lectures on atmospheric radiation, and the third module will be on cloud physics. So that makes the complete set of 12 lectures on atmospheric physics. A very important part of basics of our weather and climate science, and radiation, as you know, is the lifeline for this planet. The atmospheric systems is driven by balance in the radiation, and any disturbance which is results, as we see, in the form of climate change. And so we have now a set of 4 lectures which will be covered by Dr. Biswajit Mukhopadhyay, who had been the Additional Director General of Meteorology, and I had a pleasure to be associated with his work. The wide-ranging interest, atmospheric chemistry, radiation, climate sciences, aerosols. There wouldn't have been a better person than him to cover from practical experience and application of atmospheric radiation in weather and climate science, that is meteorology. Thank you, Mukho, for accepting our request for deliver these lectures. Director General of Meteorology, and I had a pleasure to be associated with his work. Wide-ranging interest, atmospheric chemistry, radiation, climate. How come this delayed mode? Anyway,
Yeah.
thank you, Mukho, and I'm also thankful to Singh Dorji for accepting to deliver opening remarks for this series of lectures, and of course the support of all ECT members, starting from Lakshmi, who is our coordinator of this program, Rohini, Mohan, Swagata. So thank you so much for your support to make this series of lectures. As Somesh has brought out, we know because of the time zones and other commitments, not all registered participants are able to attend, but then we support them by providing the lectures presentations and also available on the YouTube. So we request all, we'll closely follow and support you in whatever needs you have to catch up in case you are not able to attend online these programs. Once again, thank you, Mukho, Singh Dorji, and Bhaskar Rao Sahab, who is kindly is attending this series of lectures also, for providing us the guidance also. Thank you so much, and we look forward for presentations and the question answer sessions, which are very, very lively. We get good questions and in the chat box and otherwise also. Thank you.
Thank you, sir, for giving the relevance of the students' lecture series. Now I request Dr. Singh Dorji, advisory panel member of SAMA and from Hydrology and Meteorology Division of Bhutan. I request him to provide his remarks on this lecture series. Over to you, sir.
Thank you, Dr. Kumar. Good morning, good afternoon, and good evening to all the distinguished speakers, members of SAMA, and students and others who could join this lecture series, this very important lecture series virtually. Like Dr. Das introduced, my name is Singh Dorji. I'm the Chief of Weather and Climate Services in the National Center for Hydrology and Meteorology in Bhutan. and I'm also advisory panel member of the SAMA. So I would like to start with, first of all, thanking Dr. Tyagi and Dr. Sameshwar Das and the working committee and all the institutions involved for your hard work and dedication for the work that you have given to the South Asian Meteorological Association. We know that this organization is working on a zero budget and purely on a voluntary basis. What the SAMA has been able to achieve is truly amazing. So this lecture series, I believe, is one of the success stories of the SAMA. And on this note, we would like to welcome also Dr. Mukho, who will be delivering the talk for today's lecture. And on the topic of climate change, as everybody here knows that this is a very important topic. And just briefly, I would like to mention that the last 7 or 8 years has been the hottest ever on record. And as you also know that 2016 was the hottest year ever recorded. And the global average temperature, as you know, is already 1.1 degrees above the pre-industrial level. And the impacts of climate change, like extreme weather and sea level rise, and among other impacts, are on the rise. Many countries are already suffering with the post-pandemic economic recovery. And to add on this problem, then we have the climate crisis. So in this context, this lecture, especially on the radiation budget and related issues which will be delivered by Dr. Mukho, is very relevant and very important. And I would like to urge all the students and all those who have joined this lecture to take full advantage of this lecture series. And I would like to thank once again to SAMA and to Dr. Sameshwar Das for giving me this opportunity. And I would like to end here with best wishes to all who have joined today. Best wishes for the Holi as well as for a great lecture series. Thank you.
Thank you. Thank you.
Thank you, Dr. Singh Dorji, for giving these opening remarks of this lecture series. So now I request Dr. Swagata.
Thank you, Dr. Lakshmi.
To introduce today's speaker. Over to you, Swagata.
Yeah, thank you, Dr. Lakshmi. So it's a great day. So we welcome our retired MD, ADGM from IMD, Dr. B. Mukhopadhyay. His main areas of research is precipitation chemistry, aerosol measurement, air quality modeling, urban and biometeorology, climate sciences. But also he has mainly focused in the monsoon forecasting, climate variability, climate modeling, apart from radiative forcing, atmospheric radiation, etc. So today he is going to talk about that radiation budget. So let's welcome Dr. B. Mukhopadhyay for today's introductory lecture in atmospheric radiation.
Thank you, Dr. Swagata, and thanks to all the panelists who have spoken before. I must thank profusely Dr. Ajit Tyagi. I had the pleasure of working under him when he was the Director General. Those were the lovely days. Dr. Sameshwar Das, your introduction, probably that helps me to set the kind of pitch at which this lecture should be designed. So my regards to all the panelists and all the viewers, those who have logged in. Yes, we definitely would say that the physics of the climate system starts with radiation. And that's the main energy transfer process. And if you notice that the topic is atmospheric radiation. And when we talk of atmospheric radiation, we are obviously talking of the sun, the earth, and the earth's atmosphere. Now, there are a multitude of phenomena and processes that takes place when the solar radiation in its original form comes within the environment of the Earth, and certain transformations are there. Even the wavelengths change that of the radiation because of the physical interactions. And so a whole set of a radiative environment is created. And that is what is going to be the talk of these 4 lectures. And if you would permit me, I would go to share screen. And the moment if you want to intervene with a question, please raise your hand as you usually do, and I'll be responding it as and when. Right. I believe you are able to see the screen.
Yes.
Thank you. Okay, now just give me half a second. Yeah, so as I just said, that this has been such a noble gesture from SAMA to bring these lectures to you, and I hope we can live up to that sense of purpose. And we will talk about the notion of the radiation environment. So this is the first important thing for us to see, that what is it that constitutes of radiation. In the screen there is some problem. I think you are getting this obstruction. Are you?
No, I'm seeing clearly.
You're seeing clearly. All right.
Yes.
So
We are getting clearly.
okay, thanks. All right. So here is the sun and the earth. And when we talk of radiation, you see different branches of physics are there. And a lot of physicists, astrophysicists would say that radiation is nothing but streaming plasma, that is the solar wind. Because the earth lies in the environment of the sun's atmosphere. And this is a very high speed discharge of plasma particles, positive and negative, that streams towards the earth. Now, Mars, as you know, doesn't have atmosphere. The entire reason is, fortunately for us, we do have it, and we are thriving because of it. There is this effect of solar wind, which strips off the atmosphere if the planet is not able to hold it. Gravity is not enough, especially for the lighter molecules. Gravity is certainly not enough. The solar radiation, in terms of electromagnetic radiation pressure, and in terms of the momentum carried by the solar wind particles, these are extremely high velocity particles. The atmosphere is likely to get stripped off. And that is exactly what has happened in Mars, because its magnetic field turned off in its earlier stage. And the same is with Venus, which is losing a lot of its atmosphere. Fortunately for us, we have a good, thriving, healthy magnetic field, although it has a tendency to flip over once in a while, but no problems, it is still there. It's guarding against the solar wind, which would have entirely stripped our planet of its atmosphere. Right. So what it does is a little bit of physics here also. When the streaming charge particles comes with a velocity and you have a magnetic field across, and a cross product of these two, that is the Lorentz force, sends the particle perpendicular to both these fields. As a result, the charge particles circumvent the Earth and then they move away. Okay, and the atmosphere is saved. Now, this generates also this opportunity to get radiation belts. We are not going to talk much more about this, except for the fact that the Earth's atmosphere, that one that we are interested in, is something within this innermost belt. This red one is the inner belt and this is the outer belt. That means this magnetic field has trapped some of these particles from bombarding into it. So the core of this region, that is the inner black portion, is the atmosphere where we are living. And this is known as the magnetosphere, a sphere created by the magnetic field. And all we are interested in seeing that once you have got this protection of the Earth's magnetic field, and you have got the Earth's gravity to hold back most of the molecules, we have a situation where the very premise of our lecture can take off. What is our premise? That we are talking of a radiation environment around the Earth. Without the atmosphere, it wouldn't have been possible. Having said that, let me just go ahead a little bit. Now, so obviously we are talking not of any other radiation, but the electromagnetic radiation. And there's a huge spectrum from one end to the other end. I just need to emphasize, because it's known to all of you, that the shortest of the wavelengths with the highest amount of frequency, with the highest value of frequency, is on one end, and the radio waves as we know them is on the low frequency side, and long wavelength, obviously. Somewhere in the middle lies the visible radiation, and flanked by infrared on one side and ultraviolet on one side. These three together constitute of more than 95% of the total radiation energy coming from the sun, as well as what the Earth is also radiating, that is especially in the infrared. So this is again the portion of the solar of the electromagnetic spectrum that we are going to confine ourselves in. Now, having said that, just a little bit of terminology. I mean, I'm sure you would know it. There's no harm in stressing it here. You heard that use of the word hard ultraviolet, hard X-ray. We often use this in radiation terminology. Now, it's obviously hardness doesn't come from the total amount of energy that is available at this wavelength. That depends upon the number of photons that the sun is giving at that particular, and that is driven by a law which we shall see very soon. But the hardness comes from that if each photon carries a lot of energy, it can strip an atom of its inner core of electrons. Okay, it can bounce that electron off from that atom, and obviously those would be called as X-rays. If they hit these photons have enough energy to hit and knock off outer electrons, well, you have soft X-rays. Otherwise, you have hard X-rays, the ones that enter the inner shells and knock off the inner shells also. So hard and soft comes from the very famous relationship E is equal to h nu, Planck's constant multiplied by frequency. The frequency is very hard, the energy content of the photon is very high, and it's capable of doing a lot of damage to matter. Okay, right. And the soft is obviously the opposite of it, which carries less energy per photon. But that definitely must be distinguished from the fact that the total amount of energy received from the sun doesn't depend upon how much of energy each photon is carrying, but the number of photons that are coming out. Okay, so this is the only thing I had to stress on this. And having said that, can I move over to the second one, please? Yeah. Now, again, the top of this diagram is clipped off on my board. I hope it's visible to you.
Yeah.
Right. Now we will talk about the spectrum that we see at the Earth. Now, having said that the atmosphere does something to the radiation that is important for us, for our survival actually, we are interested in seeing what is happening outside the atmosphere and what is happening at the ground. It's a good learning process to see what the difference between it. And we can do experiments with satellites that go outside the atmosphere and take measurements of different frequencies coming from the sun. All right, and look at this yellow part. This yellow part. This is a very instructive diagram, a single diagram giving a lot of information, the yellow part of it. And then when you do the same measurements sitting on the ground surface of the Earth, you get the red one. Now, it's very instructive to look at the difference between the two. First of all, it has a typical shape. You see, it has a typical shape. Now, what that shape means is a part we shall address just a little later. But for the time being, let's look at the structure of it rather than the shape. Now, what this is a smooth one. The yellow one is a smooth one. Almost all the frequencies are present. Okay, almost all the frequencies are present in the yellow part of this diagram that you have drawn after taking measurements from the satellite. Measurements of what? Measurements of irradiance. And again, This word irradiance, radiance, spectral radiance is a whole array of very confusing terminology. But nevertheless, the units will help clear this doubt. And very soon, I will tell you the difference between the irradiance and the radiance and these measurements, what they mean to the different laws of radiation. Okay, but this is watts per square meter per nanometer. Let's for a minute look at this, the unit of this. So watts is power. Meter. The surface of the detector is 1 unit, 1 square meter. Okay. Then second is per nanometer. That means I have been able to split the spectrum nanometer by nanometer. And so per nanometer, whatever is the power that is coming, that has been plotted here. Well, sitting on the ground, you will find many of the wavelengths almost missing. Many of the wavelengths, on the x-axis I have the wavelengths, nanometers. And then you can also convert it into microns if you wish. But usually nanometers is considered here. Angstrom is a too big a unit. You'll run into 4,000, 5,000 angstroms for giving these values. But nanometer is a reasonably good unit to use because 500 nanometers is most part of the visible wavelength, or it is sometimes called as 0.5 microns. They are the same. Okay. Now you will find that in certain parts of this, this is obviously called a spectrum, isn't it? So in certain parts, you will find that the energy has been completely depleted by the atmosphere, because by the time it's coming down to the ground, it's something that the atmosphere has done. That's why I told you the atmospheric environment actually defines the word radiation environment, and that is the subject matter of today's lecture. So these gaps are something that are of paramount importance to us in our entire lecture series on radiation. Why this happens, we'll just investigate a little later. But can I go to the next one? Okay, now theoretically, it was known that the ideal black body at a 5,000 degrees mimics this kind of a curve. Okay, it's very close to this kind of a curve. Now, is the sun a black body, ideal black body at 5,000 degrees? Yeah, there are many ways to verify that. That's true. So what we are getting outside the atmosphere is a typical black body radiation coming from the sun. And what we are getting on the ground is typically that which is in balance with the terrestrial temperatures. That's the difference. Okay. And let's define this range as I told you. There are names given to it. And very soon we shall be using only UVC, UVB, UVA, rather than saying whether it's a short, soft UV or a hard UV or something like that. Now, nanometers, 400 to 780 is a visible range. 400 to 780 is a visible range. Most of the photosynthesis occurs in the lower part of this range and in the higher part of this range. Most of the chlorophyll has got 2 bands of absorption in this. Why I talk of chlorophyll, that is the first biological process that is triggered by visible radiation. Okay, and that's the reason why green part of it, right, the middle part of it is green, is not absorbed by the leaves, and they are available for us to perceive the leaves as green. Okay, the other 2 on the red side and the blue side have been absorbed by chlorophyll. Okay, that's why the leaves are green. Then you have the softer UV, which is very close to the visible radiation. And then as you go a little on the flanks of the band, you come to 100 to 200 nanometers. Below that, we don't call it UV. They are called soft X-rays, right? And then on the long wave side, this you get from the sun as well as from the earth. If you point it towards the sun, you get it. If you point it towards the earth, you also get it. Okay, not just the reflected one. So that means the earth is also a source. So near infrared is this, up to 3 microns. Up to 3 microns. It is about 3,000 nanometers. And from this to this is the far infrared. So this terminology is very much used in satellite remote sensing, okay, near infrared, far infrared. When you talk of radiation budget, the heat content, various parts of the spectrum, you use slightly different nomenclature. But this is a pretty standard nomenclature. And on the right-hand side, if you are able to read through it, this is these all three, UVA, UVB, UVC, are biologically important. And if for some reason the dosage of this reaching the ground increases, that's a little harmful because it can cause mutations to the biological cell. So that is why it is important. Whereas this one, visible light from the violet end to the red end, is the most significant because this deposits the highest amount of energy to the Earth's surface. And maybe whenever we talk of radiation, we implicitly talk of this portion of the radiation. Okay, right. This is a diagram which talks of transparencies, the atmospheric transparency. So obviously, this is the outcome of an experiment, how the atmosphere has transmitted in different wavelengths. You will find that the atmosphere does transmit a lot, almost 100% in the wavelength of visible light. Okay, in these wavelengths, it transmits almost everything. But in the infrared side, it drops off. And then there are certain bands of transmission. And these intermediate bands where there is no color, these are obviously absorbed. So by the time transparency increases for a little higher infrared wavelengths, we say we have the atmospheric window. This is the atmospheric window because now we are looking from the Earth's surface to the space. Here we were unknowingly talking about from the sun to the Earth, where the energy is deposited to the Earth. And then what happens is the Earth absorbs, retransmits it at longer wavelengths, and then this is where the atmosphere is found to be transmitting. And the Earth can cool itself only in this band. The surrounding regions, the radiation given out by the Earth will be absorbed. Okay, so you have a window. You have heard of this very often, the atmospheric window. Now it is this atmospheric window which is used for everything, almost everything. Satellites, they focus on these areas to be able to read what is happening from the surface or what is happening from the clouds. The Earth's radiation budget, the cooling part of it, the greenhouse phenomena, everything is in the small little piece of drawing that you have seen here. Okay, good. Now let's look at this a little closer. Let's look at this a little closer. This diagram I have taken up to 30 microns. 30 microns will practically be somewhere over here in this diagram. So from here, 10 to the minus 2 that you, minus 7 that you read here, to about 10 to the minus 4 that you read here, this entire range has been drawn in this diagram with a little more detail. Just to emphasize that, again, the transmission, okay, transparency or transmission in terms of percentage. You will find that the atmosphere is not transparent in very short wavelengths. And we know that the stratospheric ozone helps this to happen. The stratospheric ozone absorbs the radiations in these wavelengths coming from the sun. In other words, it absorbs UV radiation coming from the sun. And then comes the visible part of it. And then these bands that I was talking of, absorption bands, the blank areas are the bands, remember that. They are due to water vapor, predominantly due to water vapor. But when you come to this, again, a big area, the big range of frequencies where radiation is transmitted through the atmosphere. On either side of it is flanked the carbon dioxide band. Beyond that, almost everything else is removed by, sorry, not this one, this one, sorry. This is the atmospheric window. This wide window is the atmospheric window. And within this atmospheric window also you have a notch. Something that is absorbing is the tropospheric ozone. Okay, is the tropospheric ozone. And then there's water vapor here and carbon dioxide here on either side of the flank. You know them as greenhouse gases. Why? Because they absorb all the radiation being given out by the Earth. They will absorb all the radiation coming from the sun as well. Okay, but when we talk of a greenhouse effect, we have in mind that the Earth is not able to cool. Okay, that is our intrinsic meaning when we talk of a greenhouse effect and global warming. And that is the time when predominantly the sun doesn't have any energy during the night time. It's only the Earth's energy going out that matters. And here, if the carbon dioxide and water vapor, they are able to absorb this, they deliver it to the atmosphere. They absorb this radiation and deliver it to the atmosphere, heating up the atmosphere. Right? That's again definitely a reason why Earth is a livable place in the first place. But too much of it is bad. Now, too much of this greenhouse effect is happening in Venus today. It's got a far more amount of carbon dioxide than Earth. The surface temperatures are more than 400 degrees Celsius. So we really don't want that kind of a situation. And we are definitely much less in terms of carbon dioxide content to the Venus. But several planets, they do have a completely different kind of a radiation environment. Learning from other planets is useful many occasions. Right. Now, summarizing these two sets of information, we come up with this diagram, this notion of an incoming radiation from the sun and the notion of an outgoing radiation from the Earth. Okay, the processes have been described here. How much of them will be absorbed and how much of it will be transmitted. These two processes are there in the left diagram, but the net effect is that the Earth's radiation is in the atmospheric window, okay, where it is possible, and that is where the outgoing radiation is. It looks very simple diagram, but there are several bands of absorption even within this. Even if this band shape is known and mathematically you can do the integrations, there are so many lines in this that the total amount of energy is really difficult to integrate and find out. But, the same is true for the incoming radiation, the visible part. The visible part is very artistically given here as the Vibgyor spectrum, but you have also in the near infrared coming from the sun. Remember, this near infrared coming from the sun getting absorbed. Okay, you see these shark teeth. They look like shark teeth. They are the absorption areas. So this is the part of the spectrum that the Earth's atmosphere will remove from the incoming radiation, and they are removed by certain molecules. Okay, they are removed by certain molecules. Well, they're given over here. So why can't you use this to find out how much of what is the variability of the composition of the Earth's atmosphere with respect to these molecules, of course, right? So you can use this, and this kind of a study is called sun photometric study. You measure the energy of the sun sitting at the ground in different wavelengths, and obviously these absorption bands, they depend upon the number of molecules of gas that has been encountered. So that's a very good remote sensing technique, right? Now, so as I summarize this slide, well, you can very easily understand that the process is to allow certain radiation to pass through and not allow. And that is the essential aspect of the heat budget of the planet. And the entire system, I need to re-emphasize, the whole of biology is adapted to this kind of a environment. And today we more specifically talk of the radiation environment. Right. Now, I now move over to the next slide. Okay, now there's different parts of the spectrum have been given by these arrows. So that's pretty obvious. We've already discussed this. A little bit of statistical information for you. That's the solar irradiance. We no longer fight over this term irradiance. Okay, we have discussed this earlier. We are going to get a little more clear about this very soon. Okay, total energy from this to about 0.75 wavelength Okay, 0.57 is the end of the red part of the spectrum, 54% of our energy. Similarly, total energy from 0.39 microns to about 0.75 microns is 43%. So this is the visible light only. Similarly, total energy input from the short waves, 0 to 4, is 99%. This is called short wave. Okay. Now, total energy from 4 to infinity to the end of the spectrum is only 1%. Hardly anything to bother about, except if you are not focusing your photometers in these bands. Total energy from the 13 micrometer to infinity is 0.03 outside the window. Okay, 0.03. Now, this is essentially due to the carbon dioxide band. Now, you can convert them into equivalent temperatures. The temperatures when this energy, this is a kind of an energy environment, isn't it? Different wavelengths in different amounts. This is the energy radiation environment I was talking of. So the temperatures are related to them, okay? But they don't change much, but a lot of change in the temperature of the Earth's surface occurs due to a small amount of change in the radiation environment, if you see this, all right? This is just to overemphasize a term known as climate sensitivity to radiation. Climate sensitivity can be to any external factor. One of them is radiation. So you see that the temperature changes pretty drastically for very minor changes in the radiation environment. So these are just highlighting some of the important aspects that we would deal in radiation studies. Now come to this. Before we go into the various physical relationships, we must clear ourselves of the units. This is something which is very, very important. One second. My screen is getting disturbed. Put this somewhere here. Okay. Yeah. So there's something called radiant energy density. You look at these columns, they're obvious in themselves, joules per cubic meter. Now, this is really not of much significance, except that sometimes you would like to know the total amount of energy confined in a volume, okay, which is radiatively active. So this, for most practical use, is never we never consider. But nevertheless, there's a unit, joules per cubic meter, is the highest on top in this hierarchy, because all are derivatives from this. And then radiant flux is the power, joules per meter per second, okay, joules per second. Then is a word called spectral flux. This will be used pretty often. We'll always add a word spectral to it, and you must know what it means. The spectral flux, or for that matter, spectral anything, so to say, would be nothing but this differential. Okay, this differential is per unit band of frequency or per unit band of wavelength, whichever you choose. Many people use, people use either of them. So it's either watts per hertz, or it is watts per meter. If you're dealing with a wavelength, you express it as watts per meter, okay, or it is watts per hertz. Then comes this word radiant intensity. And radiant intensity, as you see, is watts per steradian. Now, what is steradian? Is the solid angle. Is a solid angle, the measure of the solid angle, unit of the solid angle. So this watts, imagine a point giving out energy in all directions. So each of these directions can be defined by a solid angle, isn't it? So watts per steradian. So you're looking at the directional quality in this. So the moment you talk of intensity, you talk of a directional quality. And this again, spectral intensity can have these two definitions, where it's watts per steradian per hertz, or it is watts per steradian per meter. All right. I now move over to the next slide, which talks of radiance. Now, you see, we are getting more and more derivatives. From intensity, we derive radians. Now, watts per steradian per square meter. Okay, so intensity per square meter. This is radians. So imagine the geometry. The geometry is that there is a body which is emitting radiations in all directions. So take in a particular direction, any particular direction, and consider a solid angle in which that radiation is going. And per square meter of the surface area of the emitter, that is called as the radiance. Spectral radiance will also be in similar fashion per unit frequency or per unit meter, unit wavelength. Irradiance is something which starts to integrate. We have been differentiating here. And now it's going back to as an integral form. What it says is watts per square meter only. So what have you done? You've integrated it for all steradians. So here is a little bit of geometry involved. R, theta, phi, polar coordinates, okay? And therefore, if you do all that integration in R and theta and phi, not R, sorry, theta and phi, that means in all directions, you end up with the total amount of energy given, that is called irradiance. Total amount of radiance in all directions is called irradiance. Oh, sorry. And here again, you can convert irradiance, you can use irradiance in the spectral form. So per unit measure of the spectrum. Okay. Now this is the whole set of units that are going to be considered. And you know that the differential starts from energy. You keep on differentiating it with respect to time, with respect to direction, with respect to area, and you end up with radiance at the bottom of this scale. And then again start to integrate it upwards, and then you get irradiance. Well, both these are very useful. The term radiance is used for most of the laws of physics. The term irradiance is used most for budgetary calculations, for obvious reasons. Okay, for obvious reasons. Now, just a simple example. I mean, you can pull out your paper and pencil and keep trying this. A simple example says, what is the hemispheric flux incident per unit area on a plane surface? The example that I'm going to do is the most elementary kind. In real life, how the thing has to become more elaborate, I will point out. Now, as I said, that this surface is the one on which the radiation is hitting, coming from this direction, and there's a local vertical. So this makes an angle theta with the local vertical, polar coordinate, okay? Zenithal angle it is called. And this is not only in this plane of this paper, this can come from a depth also. So in 3 dimensions. So in 3 dimensions, if you look at this, if you drop a perpendicular from this on the XY plane, you will get this line. And the inclination of this line with your x-axis is called the azimuthal angle. Okay, so this is the polar coordinate system where theta and phi are the 2 coordinates. Theta is with respect to the local vertical. What is the angle? Okay, and this could form a cone of revolution. Imagine the radiation come from anywhere in this cone of radiation where theta is the same. Theta can be the same, but yet the radiation can come from all directions, making a kind of a cone. Now, if you have to specify really from which direction it is coming, you have to also specify phi, theta and phi. Okay, so both of these uniquely define the direction from which the radiation is approaching this point P. Right, now we have set the stage for doing the calculations. The first thing, a little bit of geometry. This is that the solid angle, elementary solid angle d omega. This, according to laws of solid geometry, can be represented by theta and phi, sine theta, d theta, d phi. This is if you transform from xy coordinates to polar coordinates, you can easily derive this, a little bit of vector algebra, and d omega will give you sine theta, d theta, d phi. elementary angle, solid angle. Right. Having said this, radiance is the amount of energy that is approaching this point. So radiance N is the flux of radiant energy incident per unit area. Remember the definition, per unit area on P from an elementary solid angle d omega. So obviously the amount of energy will be called as radiance. No dispute on this anymore. Right. If we have to calculate the irradiance, as I promised you, it has to be integrated and integrated in terms of all possible angles. So you have to do this integration. Looks very friendly, but when you write out N as a function of theta and phi, it doesn't look that friendly. Fortunately for us, N appears to be a constant. May it come from any direction, it is the same. I mean, I would presume that. It's not good to presume that in a real atmosphere. But just for the sake of how the integration is to be done, I have only written this as a constant, not a function of theta and phi. The moment it becomes a constant theta and phi, you have to do a double integration in theta and phi according to that function. All right. So I split it up, at least this portion, and integration is from 0 to 2 pi. That means this phi goes from 0, makes a full circle, 0 to 2 pi, covers the entire three-dimensional space, and then theta goes from 0 to pi by 2. That is from here to here. This radiation can be grazing or can be perpendicular. Okay, it can be between any one of them. So this integration, therefore, with respect to phi includes this. Okay, d omega has been substituted over here. Very simple now. If N is constant, is not dependent on theta and phi, it is called isotropic radiation. This is a word which is used n number of times. You will come across isotropic is where it's independent of direction. So whichever theta or phi it may come from, the N remains the same. That is one thing. We can take it out of integration. Just take it out of integration. And then also using this simple trigonometric relationship that d cos theta is equal to minus sine theta d theta. You can simplify this, isn't it? So d cos theta is equal to sine theta d theta. So this sine theta d theta can be replaced by d cos theta. Good. A very simple thing this looks like now. This integration is a transformed variable, d phi being integrated from 0 to 2 pi, and d cos theta being integrated from 0 to pi by 2. This minus has been absorbed here by reversing the limits. That's all. And this you can put very easily. You know the values of the cos theta for pi by 2. And what you get is this value, which is nothing but equal to pi into n. So a very simple way that the irradiance and radiances are related only by pi. The radiance is n and the irradiance is pi into n when you have a simplest form of geometry and when you have the radiation is isotropic. If it is not so, if it is not isotropic, then this integration doesn't remain so simple. N as a function of theta and phi also has to be integrated. So it will be integration by product. All right. Now, this is just to illustrate how you really go from radiance to irradiance. Because all your physical laws are given with respect to radiance. Okay? But all your budgetary calculations are done with respect to irradiance. And therefore, at every point of time, you'll have to do this kind of an integration. This is a simple reminder. I'm sure you wouldn't like to see this. But nevertheless, as angle is described as, this angle theta is described as L by R. Isn't it? L by R. And one simple thing is integrated throughout this, around this point. What you get is theta, integral 3 to theta. And this integral theta is nothing but integral L by R. And integral L is nothing but 2 pi R by R. And that is 2 pi. So 2 pi theta is one full circle around. You know that. Now what happens in the case of solid geometry is that this angle is defined as A by R square. This omega is defined as A by R square. And if you do the same integration for doing the solid angles all around, all you get is, one sec. Yeah, all you get is the area around the sphere is 4 pi R square. So this is 4 pi. So 4 pi radian, R-A-D-I-A-N, 4 pi radians constitutes of the space all around a point. Okay. Now this is very simple, and it was just a recap for almost all of you. Right. Now, let's take a leap of faith. And why I say a leap of faith is you had done this experiment with the solar energy coming, okay? And the solar energy being plotted. And I said it looks like a theoretical curve, right? It does. After all, the sun is a black body. So when you look at the Planck's law of black body radiation, what does it say? It says that the intensity of light in different wavelengths, when it is plotted, it has a peak. It has neither not only a peak, but this peak is also dependent. This peak is dependent on the temperature. Different temperature bodies have been drawn here, 3 different temperatures. And what is noticeable is that the peak energy, there's a wavelength of peak energy, a wavelength at which the energy intensity peaks. Okay, the radiance, so to say, peaks. And this peak thing shifts to the right, shifts to the higher wavelength side when the temperature falls. And therefore the peak energy, a peak amount of radiation comes out in the green region from the sun. And whereas the green region is 0.5 microns, whereas that from the earth goes into about 10 microns or so, a little more than that. Okay, so that's the effect of the temperature of the black body that is radiating. Now, this is something that can be proved from both thermodynamics as well as quantum mechanics, both approaches. Those who are familiar with thermodynamics would love to see this KT coming in, Boltzmann constant and temperature. Okay. And those who are very fond of quantum mechanics would love to see this term H, Planck's constant, coming in. So this is finally a fusion of the classical approach and the modern approach in terms of radiation, and a beautiful law that came out from various standpoints. The standpoints of the statistical properties of the molecules, that of the statistical nature of energy transmission, from various angles. You know, this law comes absolute truth almost. From various angles you can prove this. Right. Now it says that the radiance is a function of temperature as well as wavelength. And that's equal to this. It's looks like a very intimidating function. You can basically look at it in 2 components. One is this and the other is this. If you look at this, how it varies with lambda and how it varies with t is hidden in the form of this function. Okay. This is a function of a function of a function. 1 upon this and e to the power of this. So this, the right hand side, is a function of a function of a function. So if you have to differentiate it, you have to do it 3 times. Remember that. I mean, no early warning. Why do you need to differentiate? We'll see that. The other is this one, which tells you the lambda dependence. So as the lambda increases, n drops pretty rapidly. Okay, so that means, is it that this portion of the curve is dictated by the first term, and this portion of the term is this portion of the curve is dictated by the second term? But true, where the 2 match each other in terms of strength is the midpoint. Okay, the best way of doing is to differentiate it and find out where is the maxima. Okay, the differential of this product has to turn 0. That is the maxima, and we'll do that very soon. But just by looking at it, by the functional nature of this, just by looking at it, you can say that there are 2 dependencies. One dependence that talks about an increase of radiance along with wavelength, and the other one that talks about decrease. Now, these two have to be kept in mind. And of course, it is tempered by the value of T, is scaled, so to say, by the value of T. And therefore, the T also comes into the picture. Now, having said that, a lot about the beauty of this equation. Let's now come to the brass tacks. Oh, 1 minute, what's happened to it? This is too bad. Okay. Now, this has to have some unit. After all, this unit is that of radians. So the right-hand side also has to have a radians unit, or rather radians per meter, because we are talking the spectral. We are talking about the spectral property. So we are talking of spectral radians. So it's radians per meter. And when you split it up, according to the table that I have given you, it is joules per second per steradian per cubic meter. Okay. It was per square meter, but this spectral value gave it another meter at the denominator. So it's per cubic meter. So Planck's function, well known, has got this kind of a unit. Either you call it radians per meter, or you call it joules per second per, or watts per steradian per cubic meter, whichever way you like. These are well-known constants that have been used here: Boltzmann constant, speed of light, and Planck's constant. And that helps you to find out radiance, predict, given the lambda and the temperature, what should be the radiance from the black body. Right. Associated with these two are again two different laws. One law, and both these laws, mind you, came much earlier than the Planck's law. The way we are looking at it, we are thinking that they have been derived from the Planck's law. No, they were known experimentally much earlier. The Wien's law, it says that this maxima of wavelength that we are talking of, this is inversely proportional to the temperature. Okay, this is inversely proportional, or in other words, lambda into T has to be a constant. This is what it is saying. If temperature increases, lambda decreases. That means for a higher body, the smaller is the wavelength at which the peak occurs. Clear? So the sun has to be a little bit more on the bluer side of the spectrum. The earth has to be on a little bit of the redder side of the spectrum. That is the meaning of this. Used in engineering very, very profusely. You just can't put a thermometer inside a hot oven. So what you do is to open the door of the oven, let the radiation come out, you measure it in different spectral bands, find out where it is maxima, and tell what is the temperature of that oven inside. Okay, in engineering, it has been used umpteen number of times. In astrophysics, it's one of the most important laws to find out the temperature of a sun, of a star, so to say, by seeing its spectrum. So Wien's law, which was discovered much earlier than the Planck's law, seems to be related to this. That's one thing. Second thing is there's another law that you talk of radians per unit steradian. What about all the steradians taken together? That is how the body will cool itself, isn't it? Giving it out in one direction is not enough. It gives out in all directions to cool itself. So if you are really looking at the thermal balance from that point of view, you need to integrate in terms of all kinds of directions. That is important. So there, the integration in all kinds of directions is important. And the law that comes out of that is known as the Stephens-Boltzmann law. It says that the total radiated power is a product, is a constant, first of all, emissivity, multiplied by Stephens-Boltzmann constant and multiply temperature to the power 4. Okay. Now, this emissivity and area, let's forget about these two geometric details at the moment, geometric and physical details at the moment. Let's stress only on this functional nature of the Stephens-Boltzmann law, which says that it is the constant multiplied by T to the power 4. That means the total energy can be found only if the temperature is known. Okay, so for thermal balance, this is an ideal equation. For thermal balance calculations, this is an ideal. You know the temperature, and such a wonderful tool for remote sensing, isn't it? That you can find out the temperature from a faraway place by only seeing the total radiated power. So this is a law. When you're talking about a bigger area, then you multiply it by area. This is all this is per unit area, correct? So when you're talking about a finite size area, you multiply it with area. When you are working with a body which is not black body, which is not a black body, then you have to use a fraction of the term, and that is from 0 to 1. It will vary. Emissivity, that is called. Okay. So the gray body that we are talking of here is actually a fraction of the black body, so to say. And that fraction is the emissivity. Clear? That fraction is the emissivity. Okay. Now, having said all this, there is a very interesting thing that will give us an insight into this. Let's look at this diagram once again. Two functions here. One function going in one direction, another function going in another direction with respect to lambda. Clear? Now, please remember this in your mind when we go to the next slide. This n lambda has a peak somewhere. And so the peak is where the gradient of this vanishes, right? Now, the moment you do a gradient, the differential of this, obviously, you have to hold one of them constant and let the other vary. And then you have to hold this one constant and let this one vary. So isn't this the same exercise that we were doing graphically, trying to find out where one term will annul the effect of the other term? So essentially, in mathematical terms, it is finding out the derivative of the product of two terms. That's all. And well, as I told you, this is a function of a function of a function. So there are a number of terms that will come out in the differentiation. Okay. But this is pretty simple. This is a one-stage effort, pretty simple. Now, this is the differential. It is equated to 0. The second step is that you simplify this just a little bit. Algebraically, you simplify this, bring this whole term out, put this term inside, -5 equal to 0. Now, obviously, this is not a non-zero term. The left-hand side is a non-zero term. This is an equation then. If this is equal to 0, this is an equation. But this equation is very difficult to solve analytically. And to solve this, let's simplify the look of this. All you do is to put x as hc by kt lambda. Hc by kt lambda, simply call it x. So the equation looks much less intimidating. And what it says is x e to the power x minus 1. That's all. -5 is equal to 0. Now, obviously, as I told you, this equation, rather than solving it analytically, which is an extremely difficult task, you can solve it numerically. Assign certain values of x and see. If it is going away from 0, then pull it back again by assigning a different value. Put it in a computer and keep doing it. And ultimately, you will get a solution, a numerical solution, which says that x is equal to 4.965. That means hc by kt lambda is 4.965. Or in other words, this term leads to the Wien's displacement law. Lambda t is equal to this constant. Remember in the last exercise we did this, is this constant. So lambda into t is a constant, has been derived by simply differentiating the Planck's law. So it only gives you the confidence that a more general law, the Planck's law, has got the information of Wien's displacement law built into it. Okay, right. Now, the other one, there's another exercise that you can do. Sorry, just a little bit. The other one that you can do is irradiance derived from spectral radiance. You can do that also and call it the Stephens-Boltzmann law. Now, spectral radiance can be written either lambda or or in terms of nu, whichever you choose, you can do. Any of these are valid. But please remember to transform the variables properly, because C is equal to nu into lambda. Okay, or lambda is equal to C by nu. So when nu is a frequency. Now you can convert one to the other, there's no problem. And then when you do the radiance, not the spectral radiance, the radiance, you have to integrate over all frequencies or all wavelengths, whatever you choose. And that is going from 0 to infinity. So plug in the value and again use the same trick of substituting x for a whole host of variables here. And this will automatically mean nu is equal to x kt by h. And therefore the differential now, this is important, differential now is not just differential x, but it is kt by h into differential x. So putting this back here, you get this equation, okay? Simplified form. This is the equation that you get. So by simply plugging it in. And here again, x in a simplified form will look like this, x cubed by e to the power x minus 1. And t to the power 4 comes out. T to the power 4 has already come out of this equation. Okay. Now, yeah. So when you look at this solution is something that is important. It will give you the Stephen-Boltzmann constant. Now, how do you do that? Again, you do that numerically. You don't do that analytically. Numerically, when you do it, you get the value of sigma. And that sigma is this value. So what you have essentially done is from radiance in different directions, you have integrated that into the total amount of radiance that is in different wavelengths to the total amount of energy that comes out in all the wavelengths. That is the total amount of energy given out. And that is nothing but the definition of the Stephen-Boltzmann law. The Stephen-Boltzmann law, you can multiply it with the area of the body, okay, and call it the flux, not just the radiance, but you can also call it the flux when you multiply it by the area. So, and also if you're not talking about a black body, if you're talking about the gray body, you can multiply it by the emissivity. So in the most general form, where you're looking at a gray body, you have Stephen-Boltzmann law in this form. Emissivity multiplied by Stephen-Boltzmann constant, multiplied the area of the body emitting, and t to the power 4. Okay. So you have actually derived both the laws of physics that are going to be used by us over here that we had mentioned. Both of them have been derived from Planck's radiation. Now, this was very instructive, so to say. Of practical use will be how we can make use of this Planck's law in real situations. Just a simple example I'll take, and maybe that will be the end of the lecture. Just a very simple example. Yeah. Now, I'm looking at winter and summer differences somewhere in Siberia. Why I chose Siberia is because the highest amount of climate sensitivity from this region. Okay, if the Siberian this thing permafrost melts, you have serious problems of climate feedback and so on and so forth. A number of reasons why we want to look at the very high latitudes of the northern hemisphere for understanding climate. And just to pick up an example, random, so to say. Cooling radiances in the outgoing window is what I'm interested in. Obviously, it is centered around 10 microns. So 10 microns is 10 to the 5 meter. And comparing in winter, when the surface temperature is minus 60 degrees or 213 degrees Kelvin, to summer, when the temperature is 15 degrees Celsius, and in terms of Kelvin, it is 288. It falls somewhere in Siberia, so to say, if you're very skeptical about where it came from. Here, this term beta is used to simplify this. That's all, nothing else. So this can be written in terms of beta also. But B and beta don't mix up, please. B is the Planck's constant here. Most of the literature uses B. And that's why instead of using N, I have brought in the value and the term B over here. Most of the literature that you will read will not use N, they will use B. Okay, now beta you can compute for 213 is 6.77. That's very simple with the data that I've given you. And B, if you want to compute with these two constraints, that at the window, cooling window, and at surface temperature of 213. You plug in all the values and you get this 0.38 into 10 to the power 7 unit, as we have discussed earlier, joules per second per steradian per cubic meter. Okay, so this is the radiance in winter. How much would it be in summer? The value of beta turns out to be 4.98. B is to be computed for the same window for 288 degrees now. So plug in those values here and all you get is 0.81. Okay, 0.81 of the same unit. So this is the difference, the kind of difference in radiances to be expected in the extreme ends where the climate sensitivity is very high. Okay, so 0.138 to 0.81, several times, about 5 to 6 times more easily, if not, yeah, about 6 times more. Okay, now this is the range that the radiances would take, and Planck's law helps us to get an estimate of that. Another small example of this is that a flux going out in a finite interval of wavelengths. A flux that is going out in a finite interval of wavelengths, not just centered at 10 to the minus 5. So here this is 8 to 12, centered at the 10 micron value, all right. But the solid angle is given to you, 10 to the power minus 4 steradian. This could be the solid angle subtended by a detector. You are now trying to find out the flux. Okay, you have on board your satellite a detector, and that detector would be casting a solid angle 10 to the power minus 4 steradian at the surface. Now, if this be the problem, this is typically tailored for satellite determinations, the use of Planck's law in satellite determinations, and the emitting area is 4 meters square, suppose, of the surface that you're looking at. And having said that, you can find out the flux, which is equal to 0.138 multiplied by the wavelength range, okay, multiplied by the area and the solid angle range. So if you do all the multiplications, it comes to around 2.192 in terms of watts. Clear? So what have you done is you have not bothered about which part of the wavelength, all the wavelengths involved. We have not bothered about which steradian, all the angles involved. You're only bothered about joules per second. Okay, the total amount of power emitted in this interval by this area 4 square meter. Okay, and that is being detected by the detector having an angle of 10 to the power minus 4 steradian. So this is another way in which you can apply the Planck's law. Well, the third way is pretty simple, like the first way itself, where you can apply it. And it says that computing the temperature from the observed radiance. It is a reverse problem of this. Here, the temperature was given and you found out the radiance. Now here I'm doing just the opposite of it. I'm giving the radiance and you are finding out you have been asked to find out the temperature of the, this is in remote sensing of a direct relevance. So all you need to do is to invert this equation, Now you know the value of B. You have been given the value of B, so that is measured. And temperature you can write by inverting the Planck's law over here. Instead of e to the power, it becomes log something, something. Okay. And this temperature can therefore be found out from all the values that have been given here by solving this equation. 280, it comes to 280. were earlier found to 88, very close to it, isn't it? So in the forward direction, when I gave you the temperature and you found out the radiance, you got a certain value. And then when we did the opposite of it, that I was given the radiance and you found out the temperature, we landed at almost at the same temperature. So even in the reverse mode, you're likely to get the same. In a very crude calculation, let me tell you, very, very crude calculation, a pretty good amount of accuracy you have achieved. Okay, maybe the basic laws of radiation, I would end over here. And I would now, I'm sure the panelists would allow me to answer some questions, which there could be, or whatever is the method.
Yes, sir. So we can go for the question and answer, but it will be good if you can close that slideshow. Then, if you can close the slideshow.
I am going to stop the share. Right. Yeah.
Yeah. So the first question we have received from Sajin Chatapati. One minute. Dr. Lakshmi? Hello.
Yes. Yes.
Dr. Lakshmi? So you are written. So can I start the question and answer?
Yes, sure, sure.
Okay. So the first question from Sajin Chatapati. What does it mean by reflected IR? Is it the thermal radiation reflected back from the atmosphere, or is it something else? Sir, are you getting, am I audible?
Yeah, sure.
So the question is,
yes, please.
Yeah. So the question is, what does it mean by reflected IR?
Okay.
Is the thermal radiation reflected back from the atmosphere, or is it something else?
Okay. Now, radiation emitted is different from radiation reflected. Now, every surface will have a certain property of reflection. It's called the albedo. Now, the albedo can be defined at any wavelength. Now, at short wavelengths, at IR is a long wavelength. So at long wavelengths, how much is the light reflected? How much is the energy reflected? That is the reflected IR. Okay. So all you need to do is the incoming radiation multiplied by the albedo, and you'll get the reflected value. But when you talk of the thermal radiation, is entirely different. This radiation that was coming in was absorbed by the body, in this case, the Earth, and then the Earth, in its own fashion, re-emitted radiation. Okay, so that is driven by a different law. It's not as simple as multiply it by an albedo and you will get it the reflected radiation. No. The emitted radiation depends upon the temperature at which the emitting body is. Is that clear?
I hope, because we don't have that option to interact with him. But I'm just adding one more question with this. Sir, that IR region, can we talk about that optical and then up to IR, and then we can talk about the thermal, isn't it?
Yeah.
If I break the EMR in optical, thermal, and microwave zone, so up to IR we can consider as optical, and then thermal, and the physics of thermal would be different than the reflection which you have explained.
Yes.
Okay. So we can go for the next question. It's not a very question. Can you please elaborate a bit more on the sun photometric study?
Okay. You want me to address that question right away?
Yes,
because it will be discussed in one of the later lectures. But anyway, I should be saying something a little more about this. Now, sun photometric study is from the ground. You measure the solar radiation in different wavelengths. The difference between a sun photometer and an older equipment that is called pyrheliometer is that the pyrheliometer's aperture is pretty big. It looks at not only the sun's disk, but the area around it also. But when you talk of sun's photometer, you don't want to look at the area, the radiation coming from the area around the sun. You want to find out the radiation coming only from the disk of the sun. So those measurements that look at the energy coming from the disk of the sun are called sun photometers. In contrast to the older equipments that were having a larger aperture and were looking at the sun's areole, so to say. The areole is a region around the sun from which a lot of forward scattering is taking place. Yep.
Okay, so the next question from Abhishek Loth. Using the conception, can it be told that radiation altitude or higher or harmful for humans in comparison to radiation in tropics?
Okay.
Using the concept of radiation, can it be told that radiation in mid-latitude or higher are harmful for humans in comparison to radiation in tropics?
Okay. Now, well, this is a question, harmful or not, has been addressed by biology itself in its course of evolution. The human skin color, it has adapted and neutralized that effect of difference. Okay. Now, I'll now clarify this. What it means is that it's only the ultraviolet that we have discussed is something to do with damage to biological cells. And ultraviolet depends upon the amount of ozone. And in the mid-latitudes, if the amount of ozone is more, then the amount of ultraviolet radiation coming down will be less. Whereas in the tropics, ozone amount is lesser, then the amount of ultraviolet radiation reaching the ground will be more. If the ultraviolet radiation is more, its long-term effects on skin, on the eye, retina of the eyes will be a little harmful unless the people have lived there for long and have adapted to it through the melanin on their skin, the color of their skin. They have been able to neutralize the effect of the higher amount of ultraviolet present in the tropical region. Okay. So.
Okay, thank you, sir. There are few is raised, but Dr. Lakshmi, how to take their questions? Shall we invite those people? Or? Question in the chat box.
Can you repeat?
But there are no questions in the chat box, but few people raised their hand. But I think we are unable to.
Yeah. Because we are unable to. Don't have any participants list to see here. Yeah, it is there. You can only chat with them, I think. You cannot talk to them.
Yeah.
They raise their hand, but they can only see that chat, not talk.
Yeah, so for timing, we have this much question right now.
If they have any questions, they can type. They can type, or any comment they want to use, they can type in this chat box.
But it's an interesting talk, and sir will continue. So I'm sure that later talk they will come with more questions and more doubt even from the first talk from this talk. So here I can say that question and answer session is over. So now it's Dr. Lakshmi Kumar.
Thank you, Sarita. So before going out of time, we'll have some photo session. I request all the panelists to turn on their videos.
Mohan has already shared the photo.
I think it is okay. We can take one more. Unfortunately, today in my device, my lab video option is not working. So I have to do some Photoshop later.
Yeah.
So Dr. Shagata, you can take also. I am also taking.
Yeah, I'm taking. Okay.
Just a minute.
Yeah, I have taken.
Okay, done.
It's good that you took in the beginning. Dr. Sangat Orji has already left.
Yeah, now I request Dr. Mohan to deliver the vote of thanks.
Thank you, Dr. Lakshmi ji. distinguished guest, esteemed resource persons, esteemed member of the coordination committee, and dear participants. It is with great pleasure and honor that I stand before you to express my sincere appreciation and gratitude for the successful completion of today's international lecture series session on atmospheric radiation, mainly radiation budget. This is the lecture 1 of this series. I'd like to extend my heartfelt gratitude to our esteemed speaker, Dr. B. Mukhopadhyay, former Additional Director General of Meteorology, India Meteorological Department, Pune, India. Your enlightening and informative speech has left an indelible impression on us all, and we thank you for sharing your invaluable knowledge and expertise with us. I am confident that your presentation has provided us with a new perspective on atmospheric physics and has inspired us to pursue further research in this field. I would also like to express my sincere appreciation to the respected members of the Coordination Committee of SAMA's training course, including Air Vice Marshal retired Professor Dr. Retd Tyagi sir, who is the President of SAMA, Professor Dr. Someshwar Das sir, Secretary General of SAMA, Dr. Singh Dorji, Chief of the National Center for Hydrology and Meteorology, Bhutan, and Advisory Panel Member of SAMA, for his remarks on the lecture series. Dr. T.V. Lakshmi Kumar, SRM IST, and Session Moderator. Dr. Rohini Bhawar, SPPU India. Dr. Swagata Paira, Treasurer of SAMA and from BIT Misra India. And myself, and Board of Directors and Organizing Committee for their tireless efforts in organizing this highly effective training program. Your dedication and hard work have made this program a resounding success. Last but not least, I would like to express my gratitude to all participants from SAMA countries and beyond for your enthusiastic participation and engagement throughout the program. Your active involvement has contributed significantly to the success of this event, and we hope that you will continue to collaborate and share knowledge in the future. Once again, I extend my sincere gratitude to all those who have contributed to the success of this event. Thank you. Thank you very much.
Thank you, Dr. Mohan, and I thank all the panelists on behalf of SAMA and SRM-IST. I also thank participants. So I would like to give instruction to the participants that we will have the second talk on atmospheric radiation, that is 10th week lecture on this Saturday. Okay, due to some reasons, we could organize this lecture on today. So it was supposed to be on last Saturday. Due to some reasons, we have organized the talk, Saturday's talk on today. But as usual, we'll have a talk on Saturday. That is week 10, lecture 2 of atmospheric radiation. It is going to be a much more interesting topic, that is a greenhouse effect. I think we'll have a very good information we will be getting from the speaker. I request all the participants to attend the talk without fail. So thank you one and all. Thank you very much.
I really profuse thank SAMA for this. It's a fascinating exercise that you have undertaken. I'm really finding it very interesting.
We'll stop the live streaming, right?
Thank you,
Sir, we
Mukho.
also stop the
Mohan, you
stop the recording.
Mohan, you stop
Okay.
live streaming also.